Okay, so we did the black globe temperature experiment. So, what is a black globe thermometer? Well, it's one of these black spheres that can be made out of metal or plastic. Shh, quiet. Sorry. It's a black sphere that can be made out of metal, plastic. I'm sure there are some other materials that they've tried with an enclosed temperature sensor. The first time I get at least documented that they tried to do this experiment was in 1932, and essentially they attempted to quantify the effect of thermal radiation on a human body. So instead of just using environmental temperature and other like UV index and stuff like that to be able to tell the effect on a human body, they wanted a way to be able to quantify that. So essentially, it's used to physically approximate the wet bulb globe temperature, which is an equation that takes all of these things like wind and UV and humidity and sun angle and stuff like that into account to actually measure the physical effect of the temperature outside on your body. So, yeah, it's just a more accurate representation than just like a straight up number of the ambient temperature. So it's a good thing to use the wet bulb globe temperature if you're looking at planning activities outside and stuff like that instead of just regular temperature. So how does this particular instrument work? The black coloring of the globe itself decreases the reflectivity of the surface and allows it to absorb heat, and the spherical shape allows it to do that evenly. And the industry standard that is kind of used today is a 6-inch diameter copper sphere. That's what this one is made out of. That's closest to me. And then there are also smaller handheld ones. The article that was given to us to read with our assignment was this one right here, published in 2020. And they did a comparison of two different stainless steel black globe thermometers and one plastic. And the plastic was in between in size. So they had a small stainless steel, a medium plastic, and then a large stainless steel globe. And they found that the stainless steel at the smaller diameter was the most accurate for indoor measurements. So, would you like to do this part?
Yeah. Yeah, so we tested 3 different configurations. The first configuration, we just used like the copper sphere, but a much smaller one. It had a diameter kind of like close to 2 inches. And we just wanted to test it out because the article kind of hyped up the smaller measurements working a little bit better. Our second configuration was one that you guys made, Maisie and Reagan. It was just like a cube made out of acrylic materials, and we just wanted to see like how like a different shape would affect the black globe measurements, if it would have any impact at all. And then our last configuration was just like the traditional 6-inch big sphere. And then we also just had a probe hanging out by itself, just to see if we could measure the ambient temperature of the environment, and then like compare how all of our black globe temperatures compared to just the ambient air.
Yeah, so like you said, we had 4 samples, and the conditions for our experiment was 2 full cycles. Initially, it was probably supposed to be more, but we ran into an error. 2 cycles, 4 hours each, alternating conditions every hour. So it started with the light was on for an hour and there was no fan, and then the next hour was the light is on and the fan is on for an hour. And then our third condition is the light is off, but the fan is on. And our fourth condition is light and fan are both off. And we cycled through that twice. So this is our complete data set that includes when the data or when the controls for our conditions stopped working. We assumed that it was around like this 6-hour mark. Where am I going? This 6-hour mark. So we cropped that out, and we've color coordinated what the cycles are at. So again, like the first hour is light only, as you can see. So we have 4 lines here. Our blue line is for the small globe. Our red line is for our cube that we made. our yellow line is for the larger globe, and then purple is our test. So you can see this is temperature measurements, but still in voltage, where we haven't converted to Celsius yet. And you can see that your voltage decreases when your temperature increases. So when the light's on, our temperature gets hotter, lower voltage. And then when the fan gets turned on, our voltage increases, so it's getting colder. And then when it's just the fan on, it's kind of at like a nominal steady state that is also similar to when both light and fan is off. And we see this behavior repeating. Again, towards the end it gets a little weird, so we're not sure how real that data is with the conditions we have set.
Okay, so this is a plot of the resistance across our thermistor, just as a function of time. And our circuit, I think, was pretty much almost the exact same as the radiation shield group. So this is the way that we're able to measure the temperature of the air. We just take this resistance that we calculated and turn it into a temperature. And I just included this plot because our resistance values were working nice. We see the resistance really shoots up in magnitude when the voltage goes down, which is kind of what we would hope to see. So this plot was good news, and this plot is not good news. You can see right off the bat, the temperature kind of ranges from like 26C down to 12C, which probably isn't very realistic. I'd assume that the ambient air inside of the shop is probably hanging out around like 25C. So these temperatures are a lot lower than we expected, specifically because they were kind of in that bin with all the lights shining on them. So should have been a lot warmer, but I think the air just comes from these temperature values aren't calibrated. We tried consulting Mr. GPT to define like the right values for the equation that lets you go from resistance to temperature, and this is kind of the closest it ever got, but we didn't take it a step further with trying to calibrate like a voltage to room temperature and all that.
Okay, so this is kind of a screenshot of one cycle in our data, and you can see, guys, how little changes between different devices that we are testing. So as Macy mentioned before, those are the scale. I mean, those are the different labels for the different sensors that we are measuring. But what we want to focus here is how different is the cube versus the small globe, because since they are similar size, the difference is just the material and the shape. So what we are trying to prove here is that a cube made of plastic can be as similar as a glove made of copper. So plastic is cheaper, and that's what we are looking for in the industry. So we have a little variation here on the results, but they are pretty much the same, and we don't really know if this is just because of the material, of how sensitive are the sensor. So we assume that they are kind of the same behavior, and this is for the different cycles. So you can see really clearly how they go. The temperature go warmer when we have the light on, and then start to cool a little bit down when the fan is on, and when the fan is on and the light is off, it stabilizes like at this point linear here, and then when everything is off, it's just like a line. And also we can see the difference between the small globe and the big globe. So kind of a huge difference between them in voltage, which we can translate to temperature as well. So for the second half, it's kind of the same behavior, no difference at all. But next steps could be to do this, but with the same shape sphere in plastic, but now with the big glove, because that's the reference, that's the standard, right? And see how different it can be. So our conclusions are The small cube behave very similar to the small sphere, so and it's cheaper. So that's what we are looking for. Big sphere helps faster, as we saw on the images, than the small sphere and the cube as well. And the small cube is less responsive to the temperature changes compared to both spheres. We saw on the graph how it's shifted a little bit to, I mean, this result over here, the temperature changes is the voltage is a little bit higher when this guy are a little bit lower, which means that the temperature is not reflecting how well the temperature is changing at all. Uh, Thank you guys.
Alright, I'll probe you guys a little bit. So, you go back to your temperature calibration slide for me. The one that doesn't make any sense. Or,
That one
yeah,
or
that one.
that one?
And you know that the temperature is going up there, so why isn't this inverted?
I really think we have a problem in the formula.
Yeah, I think it
Looks like
should
you have a
be.
sign error.
Yeah,
Yeah.
I think it's just the opposite. Yeah.
And you can see the different phases in this. So if you go forward a slide or two, yeah, that one, perfect. Here you have your different phases where the light's on, light's off, and you have 4 different phases and 4 different regions. But your regions don't line up with the changes that you see in plots.
Yeah.
So what is going on there?
There's a time delay, a little bit. I mean, it takes time for it to heat up and cool down.
Yeah, it does, but the sudden change in this plot is almost certainly the time of a change in the system. So right here, for
Yeah.
example, is when something changed in the system. And right here, when it suddenly goes up, is again a time change in the system. And so why isn't that exactly 1 hour?
One hypothesis is we played no role in programming the conditions.
Uh-huh.
Mhm.
Sorry, I'm throwing it.
Yeah, but that's fine. You can throw John under the bus to some extent. But really the question is, how do you fix it?
Is there a way to like set some coefficient or something to where there's like an offset?
I mean, you could match up the times in some way.
Like
You could crunch
calibrate it?
numbers.
Mhm.
But there's a better way of handling this that I don't think we ever talked about, which is sort of like a positive feedback. When you send a signal to a servo to move, sometimes you are just assuming that that servo actually moves. But it is much better to get a signal back from the servo that says, I move.
Mhm.
And so here, there is really nothing stopping you to use that system, use your data logger to actually measure the current going to the light and the current going to the fan. And then you could literally monitor exactly when the light is on and exactly when the fan is on.
Mhm.
You can solve this problem.
Yeah. I really think that um, the changes are over here, and then this is kind of response from the sensor, and then
How do you know?
because we were testing uh, the sensors, and we saw that at some point, even if we apply, I mean, when we apply the freezing air, after we stop applying it, it's still being cold
So
inside.
bring up your double plot here. You can pretty clearly see that the right-hand change is shifted to the left of the left-hand change, which indicates that John's clock is not very good, and 1 hour is not really an hour. You see that?
Yeah, maybe it's less than an hour. I think it's over here, and then it continue warming up, and then start to change the behavior over here.
Yeah.
It's the response of the sensor.
That small change might also be something like having to do with the air kicking on or off, like something else other than in our controlled environment because it was open.
Yeah, it was open
outside
also
air.
on the top.
But you don't know what the environment was doing if you don't have a measurement of the environment.
I mean, we have a thermostat on the
outside, yeah.
But we have no running record of it. Like,
And actually, if
So I don't know if getting on you guys' case, I don't really mean that, 'cause, we weren't going over this, but it's something for you guys to think about when you're doing experiments in the future is how do you measure the state of your system as well as the state of your data?
mhm,
What things do you think were the hardest about this? What things would you change if you had more than 4 hours to
to do the experiment.
defining the terms of like our question, what we wanted to ask and answer with this, and based off of the materials we had, but also the work that was already done, because it would have been really easy for us to do. There were other copper black globes out there, so we could have just like tested by size or whatever. But we found articles that were like, well, you know, the standard is the big one, but you know, they already tested like different sizes. So we wanted to do something different.
Also, we wouldn't use a window computer for our experiment. Nah, we wouldn't. We don't want that. So
Other questions?
What part of it did you guys enjoy the most?
when we were testing the sensors and saw that everything was working, the temperature were going up and down as
Yeah.
we apply heat or cold.
Yeah,
I
we
think-
did freeze spray
Exactly.
on our globes, and that's how we made the little face.
Yeah, this guy.
so that was fun. And then also at the end of the day yesterday, when it was like kind of darker in the shop and it was just the red lights, we felt like we were watching chickens, like baby chickens.
Yeah, that was really fun.
It was fun to be creative and try and figure out a way to make the temperature sensors try and be like in the middle of all these differently shaped balls and cubes and all that. That was kind of fun. You had to get creative.
And we made the cube on the laser cutter. So
Yeah.
that was super fun.
All right.